But what we're gonna do today is we're gonna talk about fuel scheduling. We're gonna deal in the beginning here with the kinds of contracts that they deal with gas suppliers. So once again, we've got a gas pipeline. This may not be the only plant that's being supplied by this gas pipeline, and this one has two pipelines, but there's a capacity. Okay, so let's put something in red here. There's a capacity restriction on the pipeline itself. We'll put two arrows like that. In other words, you can only push so much gas through this pipeline. You can only push so much gas through the pipeline, but that's sort of understandable. And by the way, the gas pipelines are very long distance. They run from the Gulf states of like Texas, Mississippi, Alabama, even Florida. They run way up into the northern parts of the United States. In addition, this is something you may not know, but there are gas suppliers in Canada that have gas pipelines that come down into none other than the state of Minnesota, and run through the state of Minnesota, cross into Wisconsin, up through the Upper Peninsula of Michigan, and down into the state of Michigan. So there are gas pipelines coming both directions into the U.S. to supply large amounts of gas. In Europe, there are enormous amounts of gas are brought into Europe from Russia. That's a major source of so-called foreign exchange, or monies for the Russian economy, is selling natural gas. during I'm chuckling because during the 1970s, early 1980s, Ronald Reagan was president, and suddenly he said, we're not going to be selling certain kind of things to Russia. He was a very hardline president, and yours truly, that's me, had a contract with a company in Europe, and we weren't selling anything to Russia, but they were imposing all kinds of rules, and this company was going to sell the software product that we were supplying to them. They were going to sell it on a system that was going to go to one of the other so-called, I use this term because it's an old, completely outworn term, communist bloc countries. Well, countries like Russia and its eastern countries around it, and we got caught up in one of these things. But it was originally because of this gas pipeline, huge gas pipeline they were bringing in from Russia. So it's a major business. Now today in the United States, we're getting gas not just by putting a pipe down into a big bubble of gas underground and then pumping it out, but we're doing what they call fracking, where they cause the gas to be released by minerals, shale, and so forth underground. And this has produced a huge amount of gas, and the U.S. is now starting to export the gas by liquefying it. They liquefy it and then they put it on ships that'll take these special containers to Europe, to Japan, and so forth. So natural gas is a big commodity. All right, so here's the other problem. The natural gas supplier would like let me say the purchaser of gas might need a variable amount. Because of the load. Because the electrical load goes up and down, and as the load goes up, the generators call for more BTU per hour, which translates down into more cubic feet of gas per hour going into the plant. So they might need a variable amount. But the supplier of gas is nervous about and would like to supply a fixed total. Let's just write cubic feet. Okay, fixed total cubic feet. And it's very interesting. They have worked on this for a while, and they've come up with a term. And the way I'm gonna show you this is that later on we'll realize that the term itself is kind of a misnomer. It doesn't really say it right. So we'll put it in quotes. A take or pay contract. If you buy gas, the initial thing says, okay, we specify, let's say Q is the original quantity cubic feet of gas. That's in the contract. It says you're going to buy so many 100,000 or million cubic feet of gas. And it's got a time on it. It's got a time. Now a timeout. Okay, so it says, let's say we're negotiating. It says by end of the day tomorrow, or by the end of the week, or something like that. So there's a time. You also remember that the supplier has to worry, as well as the purchaser has to worry about the capacity of the gas pipeline. They don't want to set up contracts that they can't deliver because the pipeline is at capacity and they just can't push any more through. By the way, natural gas, they pump it. So the first thing you do is coming out of the ground, you pump it, and it goes down the pipelines. But the pressure's dropping as you go down, and so some distance down the pipeline, might be in the 100 miles or so, they have a station that takes some gas out of the pipeline and is used to run turbines that power more pumps, and that pumps the gas and pressure back up and pushes it on down the line. So there's a series of pumping stations. Let me tell you from another. I remember listening to the chief system operator at it was a utility. It's now been restructured completely, but it used to be called Middle South Utilities. And he was complaining over the fact that if he wanted to buy a certain amount of natural gas, certain states in the northern part of the U.S. would object because the same pipelines are supplying his power plant as were supplying customers like my house here, which runs the furnace and the hot water and the clothes dryer run on natural gas. And so particularly the furnaces, you politically you can't have a situation where because of the power plants buying the gas, they have to turn the gas off on people's houses and they start to freeze and so forth. So there's a political protocol and echelon there that has to be obeyed at the same time. So that all has to do with the capacity. But let's just say a certain number of cubic feet. Now that sounds easy. You may take up to Q, and I'm going to specify the price. Now, here's the rub. Now, take or pay says if purchaser does not take Q, they pay anyway. So sometimes I used to say this should be called take and pay, but effectively what it says is that you agreed to take Q, and suppose that the load is down and so forth and so on, and the purchaser says, yeah, I know I agreed to buy Q, but I don't need it, and the supplier says, that's too bad. You're going to pay for that. You're paying for the whole contract. And whatever gas you don't take, the purchaser can now deliver to somebody else. One thing that is also part of this, the natural gas system is a nice system for the following reason. The natural gas system, you've got a gas pipeline like this, and you can have a pipe that just goes down into a big storage tank in the ground. Well, they don't build a tank out of cement or anything. It's usually, it might be an abandoned mine, for example, where they can pump gas into it and build the pressure up, and it doesn't leak out. It's hundreds of feet below ground. And so they can pump gas in, then later on they can take it out. So it's storage. And storage means that they can be running the pipeline off hours into storage near the load, and then take it from storage. So if you're running a power plant over here, here's our power plant, and we've got a contract to buy here. Here's our pipe coming in, and so normally the gas comes down and it comes into the plant, but we contracted to buy so many cubic feet, and we're not going to be able to use it by the end of the contract. Well, the supplier can then put it into storage and sell it to somebody else. I mean, it seems unfair, but that's the way these contracts are set up. I was looking at Wikipedia as a little discussion of it, and they put out the fact that once you decide to say I can't buy all the Q, then they may charge you a slightly lower price, but you still have to pay for the gas that you didn't use. And so it pays to schedule things. Okay, so the important takeaway here, we'll put a little star, is that we need to schedule the power plant consumption to use cubic feet in the time period of the contract. We'll put a little exclamation point at the end there. So you need to make sure that you use the gas, because if you don't, you're still paying for it. So that's like taking money and just throwing it out the window, if you will. It says I'm not going to get the gas. The supplier is going to give it to somebody else, but I got to pay for it. It's like paying a penalty, and you don't want to do that. That runs your whole plant efficiency, your whole system efficiency down. So this is a very important thing on gas. Now you still have similar problems with fuel scheduling. Another one, and we have a homework problem. I will talk about this week's homework. If you have a tank at your facility, and we'll put the standard stack here, and so we've got oil coming up in a pipeline. Okay, so we're getting this oil, and we're pushing it through, and we can put it into a tank, and then we can use it at a greater rate than the oil can be delivered in the pipeline. So this is a scheduling problem that we'd like to work on, and you understand here in this case the oil tank is owned by the power company, and the other vestige of this kind of scheduling problem is here is a great big coal pile, and I mean big. I mean, you don't go out with a bunch of guys with shovels. You have big bulldozers that go out and move the coal around, and then the coal runs on a conveyor belt into the plant and into the place where the coal is probably pulverized and burned in the plant. And so here's this coal pile, probably supplied by rail. So here's my little childish drawing of a train with hopper cars, they call them, that are delivering coal. Okay, so this is delivered on a train. If your plant is near a river, they will deliver coal on river barges. I don't know if they still do that on the Mississippi or not. They certainly used to. And then one of the hazards, and it's a hazard for the train too, but especially for the barge traffic, is to get the coal through when the river might freeze. And if the river freezes and you can't get the coal, then you got to shut the plant down. And I know that I remember talking to electric utility people at times in my career, and they would say, let's darken it here, and then there's the coal gets delivered into the plant on a conveyor system. These coal piles are enormous, and they may build them up over months during light load periods to then to be able to use them to deliver that coal into the power plant. So there's scheduling of the coal pile. There's scheduling of an oil tank. We could write this here: oil tank. And to some extent, but generally the storage is owned by the gas company, not the power company. So the gas company stores and releases gas for its own purposes, and you don't get to schedule it. Okay, so this is the so-called fuel scheduling problem. Now, without going into it too much, I'm gonna go into the Lagrange formulation. Okay, so we're gonna have a whole bunch of power plants over here, and they're going to supply power into the grid. And then I have another one over here I'll call that T. That's my take or pay. Take or pay, as I said before. Take and pay would be a better way, but this doesn't ring. So anyway, take or pay is this T unit here, and it's also supplying power into the grid. And we're gonna, let's say this goes 1 to N over here, And the Lagrangian is going to say, well, look, it's the same problem that we've always had on plants like this, where we just have Fi of Pi. There's a new variable that comes along, and the fact that we're going to be optimizing over a time horizon, okay, and I'm going to say j equals 1 to, let's say, a time horizon like t, I equals 1 to n. I'm going to have an n sub j. And n sub j is equal to the number of hours in the period j. So, for example, I could have 4-hour periods. So I'd have 6 of them per day. Or I could have 8-hour periods, just 3 per day. I could have a daytime, an evening, and a morning time, just to have 3 different periods during the day. Or you can go right down to 1. You can have 24 time periods and so forth. So that's that says minimize, do the standard economic dispatch up here. And I'm going to have a lambda for each period. This is a lot like the unit commitment, j equals 1 to t, and I'm going to say lambda sub j times p load j minus the sum I equals 1 to n pij minus ptj. Well, this is p of t coming out of the take or pay plant. So that all the generation must equal the load. Same old thing we did before. But now I'm going to add another constraint that looks like this. It's got another Lagrange multiplier called gamma, and I'm going to multiply that, and I'm going to say over all the time periods, j equals 1 to t of nj q, okay, q of tj minus, and you can write it as I wrote it in the text, we'll write it this way, q total. So this is the constraint. We'll put this in red. This is the take or pay constraint. And it says over this time horizon t, and Q of t is the amount of gas. So let's draw that over here. So here's gas going into the plant, and it's going to draw Q of t, which is the quantity that this is cubic feet per hour, and that's a function of P of t of j. And it simply says I have to have a function like this, and so this I should have put this in here. I should have put Q of t of P of t sub j. So that says I sum up the gas used in each of the time periods times n, and I add that all up, and that better equal the total. If this is 1 day or 1 week, whatever the total time is, that's the contract amount. Okay, we can put this in here with with a star. Contract, right there. And you notice that I don't have a fuel function for this, because at the very beginning I agreed to pay a fixed dollars for Q total. I'm not gonna go back to the example where the rate that you pay for the gas, if you don't take all of it, that it changes or something like that. Let's assume that the gas company comes to you and says, you know, they call you up and say, have I got a deal for you? I'm willing to sell you 2 million cubic feet by tomorrow night at so many dollars, period. And your buyers who are on the phone with that guy have to decide whether or not to take that contract on. And these contracts worth tens of millions, if not hundreds of millions of dollars, are literally made over the telephone. They're made by, they're not even made over a handshake or an actual signature. They're made by voice. People agree to this system like this. Now, given today's ability to send emails and documents and things, they would probably do all of this negotiating on a web page, and there would be electronic documentation, so to speak, that they would have. But in any event, all that contract negotiating is done very rapidly, and once you agree, the gas will start to flow at the right time, and you want to operate it. Now, if you set this up, the difficulty with doing it this way, the difficulty, I'll just write this down, and we'll move on here. You adjust gamma up and down. Well, you notice that gamma is multiplied times the sum at NJQ of P of T. Well, when you work out all the units, the dollars and so forth, here's Q total. This looks like the sum NJ gamma times Q of P, and this is so many cubic feet per hour, and this thing comes out to be the units of dollars per cubic feet. So it looks like a fuel cost. It looks like a fuel cost, and that's pretty much the way you understand it. Is that gamma is a shadow cost. Some people call it a pseudo cost, and what you have to do is adjust gamma up or down until you get the schedule that you want. That doesn't. The gamma doesn't have anything to do with actual fuel costs. It's a number that you're trying to adjust until you get this whole thing scheduled perfectly. It's not a great way to do the problem, but it at least helps you understand that you can solve it with the Lagrangian method. You see, and at the beginning, I guess I'd have to look at. Suppose the Q were a linear function. I mean, that were quadratic. Whether or not this whole thing devolves to a set of linear equations, it probably does in that case. And you can solve for lambda for each hour and Q, except Q is, no, you can't, because gamma, this constraint spans all the time intervals, whereas once you fix the value of gamma, then you can separate all the other economic dispatch to one per each time period, given the value of gamma. But picking the value of gamma is not easy. It's similar to the problem of Lagrange relaxation. You pick a gamma, you schedule it, and if you're using too little gas, well, let's put that down. So if you pick gamma 0 and uses too little, okay, so the sum of the NJQ of PT is much less than Q total. Okay, if that's the case, well, you didn't use enough of the gas, okay? So the thing to do then is to say, if you think about it as a cost, lower gamma. That makes it look cheaper. It makes the gas generator look cheaper or less expensive, and that will use more gas. And so let's say lower gamma, and that becomes gamma 1. And so now this sum NJQ of PT is, let's say, is slightly greater than Q of T. Okay, now at least you have a bracket. And so now you say, well, it's greater, so then I will decrease to gamma 2 again, and hope, and I keep bumping around to get this close. And it's similar to the problem of adjusting the lambdas in the unit commitment with Lagrange relaxation. It's very sensitive, and it can be I've given homework problems and sometimes exam problems, and I don't like to, because the value of gamma, in order to get even close, you might have to be getting down to the point where you're adjusting in the third decimal place. That is how sensitive it gets. But anyway, that is a means of solving it. That's a way of showing it in a mathematical solution. And it gives you this pseudo price idea that you put a pseudo price on it to give you the schedule that you want. Okay. So the next thing I'm gonna talk about is my little choo-choo train problem. I drew the figure for the slides that we have on CUSP. You have these slides, and the little figure didn't get in the textbook, so I'm going to use it here. The idea is this: I have a coal mine, and I have a train that goes out, and it goes out once a week, and it stops at the first plant, and there's an unloader here, and it unloads a certain amount D, and that goes into the coal pile, and there's a volume in the coal pile, and then there's a generator in here, and it uses coal and generates a certain amount of power. Then the coal train goes to the next power plant and unloads the remainder. The deal is that whatever comes in, he has to unload all of it, either most of it here and then the remainder here, or vice versa, or equal, it doesn't matter. So there's a D1, V1, and a P1, D2, and so forth. And he goes around for three weeks, and there's a schedule of power over those 3 weeks, and the problem is purposely set up for linear programming, and the neat thing is not so much that I can set it up as to see what you can do with it to understand what's happening. So we have load that looks, there's 3 weeks, 1, 2, 3, and it's 1200 megawatts, and then it goes way up to 1500 for the second week, and then it comes down to 800. Now this is looking at it, saying for a whole week the power is just constant. Yeah, well, let's say it's supplying this into a large system, and that's the contract for those 2 plants that it supplies. Incidentally, there's a very, very large coal-fired power plant west of the Twin Cities, west of Minneapolis here. If you get on Route 94, if you look on the map, look on Google Maps sometime, and you get on I-94 and you start driving and you go to the west, and you're going to get on you're gonna come past St. Cloud, Minnesota, and then to the west of St. Cloud there are two generating plants that you can actually see if you know where to look. They're to the north of I-94. One of them is a nuclear power plant, Monticello, that's the name of the town, and there's also a very, very large plant called Sherco, which is a wonderful example of a very big power plant, and that plant Sherco has got about 2,400 megawatts of capacity. And so they actually, I believe, have 3 generating units in the plant itself. They've been having, they had some problems with one of their turbines a few years back here, so they're not under full capacity. But that's one of the coal plants that they have not converted to natural gas. They're still operating it as a coal-fired plant. They bring the coal in by rail, and but that's a 2,400 megawatts at one plant is a big plant, is a very big facility. All right, so I've got these two plants, and they each have the one can go from 150 to 600, and the other one can go from 400 to 1,000 megawatts. So we'll call this P1 and P2. Okay, and we give you an F1, which is a linear function, and F2 is also a linear function. And then we also, from this, we can calculate a Q1 of P1 and a Q2 of P2. How much coal does it yeah, this is in tons per hour, and then we can start setting up constraints. And we set up constraints such as P1 of hour 1 plus P2 of hour 1 equals 1,200. And similarly for P1 of 2 plus P2 of 2 equals 1,500. P1 of 3 plus P2 of 3 equals 800. So those are the loading constraints. Now, we say that the train carries 40,000 tons in the hopper cars. Incidentally, what also makes this a very interesting problem, as far as I'm concerned, I didn't say this and I possibly should have. There's a name for this kind of train, where it's a train and it's got nothing but coal cars. I'll write it on here. It's called a unit train. We'll put it in quotes. Look that up on the internet. Look it up on YouTube, and you'll find they have movies of these unit trains bringing coal to power plants. Trains that are hundreds of hopper cars long. They load them up with coal at the coal mine, bring them to the power plant. It's called a unit train, and it does nothing but haul coal. And so it carries this much. And so we say then, well, the delivery of coal, then D1 of 1 plus D2 of 1 must equal 40,000. We're going to deliver, and we have one for D1 of 2, D2 of 2 equals 40,000. etc. D1 of 3, etc. equals 40,000. Now we'll write it in there. D3 of 3. Okay. So I'm going to deliver 40,000. It doesn't say, and then we're going to put limits on how much can be delivered, and in the text we formulate all of these equations, and we end up with a tableau that looks like this. It's in the text. This is right out of your text. And here are all the constraints. And you can go through this, 12 constraints. And you'll notice that some of these, and then I named the variables across the top here. Variables. Oop, let's pull that out so you can see it. So there's the variables going across the top. And you can see them listed off over here. So if we turn it this way, there's D1, P1, D2, and P2 with a 1 subscript, that meaning this is the hour 1, or it's period 1. Period 1, period 2, period 3. And then there's certain ending conditions, and there's certain restrictions. So these are all the linear constraints. There are constants in the linear constraints. There's a couple of constants over here. Let me put this in red. Right here, these are coal pile initial conditions. Initial size, let's put it this way, okay? So that if the coal started out at a different size, and we told you that it starts at a certain size. And down here we have the limits, the upper and lower limits. So these are the variable min and variable max. So these are the upper, lower limits on the variables, and that's all in the text. Then what I did, and I don't have a copy of it to put up on the screen here, but it's already loaded, or it'll be loaded on in the homework 4 directory. I'm going to give you a MATLAB program that's got this basic tableau built into it, and it solves you have a MATLAB code that solves chapter 5 example 5C. That's the first, that's the basic LP problem. And then the homework asks you to go look in the back of the book, the back of chapter 5 in the textbook. There are 3 problems that ask you to make some sort of change to something. And you have to figure out how to do that and solve. And once you do it, you just change the numbers in the tableau or wherever you can change the limits, you can change these initial conditions, whatever, and you can then resolve the LP, and from there you get an answer, and that's really, so it's an exercise in how to recognize what to do. So it's kind of a trivial problem. Well, yes, it's trivial, but the point that I want to make about this problem is that if you're a group at a large generating company, and you're dealing with several different gas suppliers, they call you up on a Thursday and they say, "Hey, have we got a deal for you? We're going to sell you so many million cubic feet at this price. Must be consumed by Friday at midnight." and starting Friday at the beginning of the day. So you got 24 hours on Friday, and you got to use this up. Do you want the deal or not? And you have some time. You say, well, we'll get back to you here in an hour. Okay. What you would probably have is a code, a large LP code, and your people would go in and they would make database changes and run the code, which simulates your whole system, and maybe they would simulate it with several different alternatives to see whether or not that is a good deal or not, or whether there's a big risk. You can take some of the values like the load, and you can say, well, we're gonna study the load at the projected or predicted amount, the forecast amount, and then we're going to raise it up by 10% to see if the load goes way up because it's a real cold day tomorrow. Are we going to be in trouble and lose a lot of money because we didn't have enough generation on it, we had to buy it, etc., etc. So you would run studies as quickly as possible before you make the decision. These are multi-million-dollar decisions. You want to know pretty quickly, is it a good decision or not? So that's the kind of thing that this little LP problem is all about. All right, now the other problem that we're gonna study in doing this is a problem where you have let's see, this is, I'm sorry, I'm trying to keep the page numbering. 5. You have a pipeline, and in the pipeline is going to deliver a fixed amount. So there's a fixed input per hour, fixed barrels. BBL is the abbreviation of barrels per hour coming in. I think it's 500, whatever the number is, and that's fixed over the time horizon that we're going to work with here, and we're going to say that this thing starts at 3,000 barrels in this tank, and there's a Q, which is a function of P, and this is putting out P, and then there's a given load to be scheduled. And I want you to use dynamic programming to solve this problem. So let's start out and talk about use DP. So the state that we're going to use, the state is the volume of oil in the tank. Volume of oil in the tank. And what I'm going to say is, well, and we'll start it here on the bottom of this page, and I'll come back up to the top a little bit. So I want be able to draw this big. So I'm going to say here is 3,000, and I'm going to allow you to consider. So these are the states. These are the states. Are the volume in the tank? Okay. That's the volume in the tank, and it could be 1,000, 2,000, 3,000. I don't want you to worry about it going zero to zero. We're not going to let it go down that low. And it's going to start right here. And so we're going to have period 1, period 1, 2, 3. This by the way is problem. Let me put it up here. This is problem 5.6 in the text. Okay, and I want you to use DP. So in this instance, we're going to use dynamic programming, and we're going to say we've got a fixed amount coming into the tank. Now let's talk about the states down here. I will redraw this a few times, but let's say the tank is sitting at 3,000 up here, and in period 1, the plant uses oil exactly equal to the inflow. Okay, so this is the inflow up here, inflow. So it equals the inflow. Well, then what is going to happen to the volume in the tank? It's going to stay flat. Okay, so the amount of P, it says plant uses it, so that says that let's say R equals the inflow, and in this case R equals Q of P1. So whatever Q of P1, whatever it equals R, well, that means that the volume never changes. The oil comes in and it goes right into the plant, and the level of the oil in the tank stays constant. All right. Well, let's suppose on a different note now that in red here I'll have period 1, plant uses greater than the inflow. Okay, so that says that R is less than Q of P1. Okay, so the inflow is less. What is this thing going to do? So that it says that the plant uses an amount greater than the inflow, or the inflow is less than what's going to happen? Well, it's going to go down. Okay, it's going to go down here. So this is where R is less than Q of P1. And let's see if we could use this color. So I'll use a green up here, and I'll say, okay, suppose for period 1, R was greater than Q of P1. So inflow is greater. Well, if the inflow is greater, then the tank is going to fill up. Okay? So here's where R is greater than Q of P1. So once again, the volume can go up, the volume can stay constant, or it can go down. It can go up if I'm not using the fuel as much. And in fact, there's probably a possibility that this plant is operating against other plants, so you could say let the other plants supply the load. This plant doesn't operate, so that the inflow just fills up the tank, and that's the green. Black says it uses exactly what the inflow is. Red says it uses less, so it's drawing the tank down. Okay? And what this problem is concerned about is it says, okay, you're going to start here, and at the end of period 2, you're going to end here. So we have states that represent dots, just like we did in the unit commitment with dynamic programming. And now it's a matter of finding a path. So I could do something that would say, well, this could go up like this, or it could go straight, or it could go down like that. Now it turns out that you can't bringing it down. You can't operate Q such that you bring it all the way down to 1,000. But now you have states in it, and the states could go down like this. They can go down. Let's say it can go down. This probably could go down like this, and so on and so forth. So it could go up, over, down, and so on. Just like the unit commitment problem. And each of these decisions means that you have to work your way over, but we're going to end up here. We're going to end up with the thing coming, and we're going to trace the least cost path, let's say, back through. I'm just drawing a kind of a random one here without, this isn't the answer. What is the best path to give me the cheapest cost? Now, what's built into the problem, what is so nice about using dynamic programming here, is that this might be the max for the tank, and this might be the min. We never want it to go below 1,000 or above 4,000. So by using this state method here, I've automatically scheduled it to obey the max and min storage capacity in the tank, and I can schedule. Remember, I've got a different load in each of these time periods. So the power plant that's operating here and the other power plants, there's an equivalent for the other power plants, and so they operate against each other. Let's draw that. So I have this tank one here with a tank coming in. And then I have several other power plants that I just draw like this. And I lump this into one equivalent big plant. And I give you an F of P over here. And this is P of T, or it's the equivalent of all the rest of the plants. It's sort of an equivalent of your net generation and the rest of the. And this is the P for this plant over here, and you're trying to minimize the overall cost of doing this. Now with the oil, if you have a contract that says the oil company is going to deliver so many barrels per hour down that pipeline, I've paid for it. That's fixed price. So I just need to make sure I don't use too little or too much from the tank. So I got to keep it within these limits as I go across here, and I've got to follow a path. So remember, if it ends up going up, that means I'm not using as much as it's delivering. If I come down, then I'm using more than it's delivering, or I can go flat, which just simply says I'm using the exact inflow. Now what we're going to see, to be honest with you, is that there's a very mirror image of not a mirror image. It's the exact same procedure with a few more complications for hydroelectric, where instead of a tank, we're going to see in a hydro plant let's get this hydro. We have a river coming down here, and we have inflow, and we have a big reservoir sitting out here, and we have, here's our hydro plant here. This is the impoundment. Here's our reservoir that has a certain volume in it, and it has a V min and a V max, and there's a certain Q coming out, which is a function of pH, the hydro. But what makes a hydro system very interesting is that we can have two of them in series. And here's another one down here. So here's plant number 1, and here's plant number 2, and the inflow to this one is equal to the outflow of this one. Maybe there's some other streams coming in. The system in California, it's about PG&E. I was acquainted with an effort that went on in the 1970s and early 80s of writing a complete hydro scheduling code for all the hydro systems in California. Very complex system. I also saw the effort that went into a hydro scheduling program for the Spanish system in Spain. So there's an area in Spain called Iberdrola, which is a northern Spain with the Pyrenees Mountains. They have unbelievable complex hydro system up there. So we're going to get into that next week. I won't go on into too much about hydro, but you can use similar dynamic for scheduling hydro systems. So I want you to see that oil tank problem as a similar problem where you have storage, and you just make the volume in the storage as the state for the program. Now, if you have to have nonlinear functions and you have to have a lot of very fine granularity in the problem, well, then you instead of having 3 or 4 states like I did, you could have 50 or 60 states. But now dynamic programming gets excessive, and you're better off with a linear program or something like that, which we will also cover next week. So your homework 4 is going to cover LP fuel scheduling, and it's also going to cover a dynamic programming, fuel scheduling. And then homework 5 will deal with hydro scheduling. Look at this thing. It didn't. Come on, refocus. There you go. There's a button on here. It says autofocus, and it seems like it goes to sleep. I don't know why. All I know is that if I put my hand under it and move it up and down, that seems to wake it up. And so you get you're gonna apply LP and dynamic programming to doing a fuel scheduling, 2 different kinds of fuel scheduling, and then the homework next week, number 5, will have to do with hydro scheduling, and that will the 2 lectures on hydro will then complete this section, and basically that will complete the section on generation. So we talk about generation, energy, scheduling, etc., economic dispatch, unit commitment, fuel, and or hydro scheduling. Okay, and that will be the end of a section in this course, and then we will pick up, start picking up sections on how do you schedule these things when you have a transmission system. And you just can't do whatever you want to do with the transmission system. It's got capacity limitations, and it has problems of the fact that the transmission lines are up in the air where they can get hit by lightning, they can get knocked down by weather-related tornadoes, whatever, and so we have to worry about outages and how do you schedule it safely. And so there's a whole section coming on transmission systems. I'll just give you a little website. So there'll be transmission, power flows, and there's a whole section on that, and then we get into markets at the very end of the course. So that kind of divides the course. There is something on fuel schedule, not fuel scheduling, on load forecasting at the very end, and if we have time, we'll get into that too. Okay, so we will call this a day here. The second homework is now posted, as well as a solution. So is the first. Once I post the homework solutions, obviously I cannot take anybody's late assignments. The TA and I are going to be a little more strict on and not, I want you to finish your homework. You're being given the homework on a Friday. It's not due until the end of the week on the next week. That gives you a full weekend plus the whole week to do each homework assignment. And please don't be coming and saying, I know we had somebody at the very beginning, I understood that, but don't be requesting. I'm falling behind. Now, if you're sick or something like that, get a hold of me and we'll talk about it privately. In any event, I can always, for example, if you're sick and you can't do the homework, I will simply say, okay, you get me some medical excuse, and I can simply say, okay, you're excused from doing those, and your grade will be based on the remaining homework. Okay, we can do that, but that's not something I like to do. But, your graduate students, the difference between graduate students and undergrads should be that graduate students are far more mature. You're into your graduate studies. You've been shown to be able to do very good work, and we shouldn't have to have too many difficulties with you, but things do come up. Okay, we will see you all next week. So I shall now leave the meeting, end the meeting. There we go.